You record. Hi, are you new? Have you? All right. So you're the person who emailed, right? Okay. All right. So let me give you. Sorry on the blackboard, but I'll give you. Uh, so this is gonna. So well, so that and just put it in front of you. So when I talk to you, I can call you by name instead of having to point at you or something. Uh okay. Um. Okay. When I was talking to her, that reminded me of something else, but um. That what that was too. Yes. So the role I'm going to pass out here in just a minute, probably pretty soon because everyone has probably everyone is here now. I'm going to give you another sheet of graph paper because we're going to do some things today. So make sure that you have enough to write on. And not using if that's save it. Number three. Okay, yeah. So that's 17 had a question, and it was a question that I remembered some point here over the weekend. So it's not difficult, but it's annoying. Something I forgot to mention. Let me open this one. So I think you're just putting a vector in component form. Did I scroll past three? Here's three. All right. So that one. All right. So they're giving you initial and terminal point there. And all they want you to do is put that in component form, right? Okay. So remember, that's very easy, right? You're just going to take the difference in the x components, right, or the x coordinates of these points, right, and the difference in the coordinate of these points, right? Sort of like you were computing slope, and then that becomes those two numbers become the two components, right, of the vector. So the difference in the x coordinates, right, is the horizontal component, right, and the difference in the y coordinates is the vertical component. But apparently at the end, I thought they asked you this. Oh, to write it as a linear combination of the unit vectors, the standard unit vectors I and j, right? So you're going to put it in standard form, in other words, right? Okay, and that's once you have it written in component form, right? That's very easy to do, except for a catch here in WebAssign. So let's see what is it. Let's see if we can do this just in our head, so I don't have to write it down. So the I component there, right? The horizontal component is going to be -2 -0, right? So that's -2, right? And then the vertical component will be -1 minus a -5. So that's -1 plus 5, which is 4. So -2 and 4 for my version of the problem. Yours might be slightly different. Okay. And so let's enter in component form. So you do have to include the pointy brackets, right? Because they did not include them in your answer. But you do want to watch out because sometimes in WebAssign, they will include the pointy brackets in the answer, in which case you just have to type in the components, right? And sometimes they leave the pointy brackets off and you have to type those in. That can be really irritating too, because you'll be typing in what you know are correct numbers, right? And you'll be wondering, why is it not, how am I not formatting this right? So watch out for that. Let's see. So let's just put in the pointy brackets there and type in the numbers, which I already forgot now. What were they? -2 and 4. So -2 there and 4. Okay. So that's all easy enough, right? And then now we want to write the vector in standard form, which means, right, as a combination of multiples of the standard unit vectors I and j, right? Remember, I is 1, 0, and j is 0, 1. So you can multiply those vectors by the appropriate scalars and add them together, and you'll get just another representation for this same vector minus 2 and 4. Okay, so that linear combination is pretty obvious, right? It's going to be minus 2 times I, right? And then plus 4 times j. The problem is that the I on the keyboard is not the standard unit vector I, okay? So you cannot use the I off the, so that's the nasty part. So is that in, where is that? Oh, there it is. It's still in vectors, right? So there's I, and then what was it? Plus 4j? Let's see. Can I get a plus sign off of the, that you can use from the keyboard, but you can also get it off the palette as well. So plus 4, and then back to vectors here, and then we want the standard unit vector j. And so Fatin was complaining that he had burned up all of his tries, trying various combinations of of this same answer, and that was what the issue was. So sorry about that. Oh, by the way, notice, so what we're going to start seeing today is here's a third standard unit vector k, and that's because we're soon here to switch to 3 dimensions, right? And in 3 dimensions, we have 3 standard unit vectors, okay? And the third one is usually labeled k. All right, let's see if we got that. Well, we didn't get all of that right because I didn't answer everything correct, but did we get those 2 pieces right at least? So remember, you can submit multiple times and sometimes with partial answers. Yeah, so we got those 2 correct. But every time you submit, you're burning up your tries. So Fatin, if I remember, so perhaps you would send me an email, or you can send me a message through WebAssign as well on this particular question, right? Remember, you can ask your instructor, but you can just send me a regular email, right? And I will add some tries so you can go back and fix that answer. Okay. All right, so don't forget about ask your teacher. That's so if on that problem is a good example of that, Fatin. So if you're burning up tries and you're wondering what is going on, because I know I have the right answer, use that ask your teacher, and then I can see a copy of the problem, and then I would have probably figured out that you were using the wrong symbols for I and j. Okay, now here at the bottom, what I was thinking was, some of these problems at the bottom, right? Oh, like this one, 12 and maybe 11 also, because we haven't done that example. And then especially the last one here about force, because we have 2 examples on force that we're going to do, right? So those 2 problems we haven't seen examples of. So if you were scratching your head on how am I supposed to do these things, then, well, we're going to learn pretty quickly here, right? Okay, how to do that. Any other particular questions from the homework that you recall so far? Okay, I didn't look at any scores, so I don't know how much work y'all have done yet, right? But so in other words, do midnight on Wednesday. Okay, so we still have another class meeting. You still have a chance to ask questions before midnight on Wednesday. All right, let me find the notes. Here we are. Okay, so this is where we finished last time, sort of, and I don't think we had gotten to example 3, right? I don't think I have anything written. Oh, I don't have anything written under example 3. But I had added in an extra part here to example 2 because we're going to use this for recall practice today. So we're going to do this problem first, but you're going to do it. But let's try to do it in pieces because you probably have forgotten this example B, which is what this C would be based on, right? Okay, which is fine because it's a little bit of a complicated procedure here. But so we want to write down here. Oh no, what we want to find is the direction of this vector, right? I want to find the direction and also the magnitude, but we'll have to compute that along the way anyway. Okay. So what's the magnitude and direction of this vector minus 7i plus 5j, right? Okay. And remember, the way you do this is you'll take this vector v and you want to write it in this format. Okay, which is also standard form because notice it's just a combination of the vectors I and j, right? Except the coefficients on the I and the coefficients on the j are written in a little bit special form, right? Okay, you have the magnitude of the vector times cosine of theta, where theta is the angle formed by the vector when it's in a standard position, that is when it's starting at the origin, and the x-axis, right? Measured in like you would in trig in counterclockwise. The angle is measured in counterclockwise direction, right? Okay. And so once you have written this, for instance, this coefficient minus 7, once you've got it written in this format, then you'll know what, of course, you'll know what the magnitude is, but we're going to compute that first. And then, but you'll know what the cosine of the direction of the vector is, okay? And then once you know the cosine of the direction of the vector, then you can figure out what that angle is, right? Okay, by using inverse cosine, correct, or arc cosine. So that's what we did in this example last time, but we didn't get a chance to practice that. But so I want to give you an opportunity to practice it. But since we're since we're 5 days later now, right? It's going to be it's going to be a challenge, right, to remember some of this. But that's all right. I'm going to help you. We're going to take it step by step, right? All right. So there's the vector. My first suggestion is to draw a picture of the vector. Okay. So on your graph paper, sketch a little, rough set of axes there, x and y axis, and draw a picture of that vector minus 7i plus 5j, right? Okay. So this means what? The horizontal component is minus 7, right? And the vertical component is 5. All right. So see if you can draw a picture of that vector. And then you want to compute its magnitude, right? Because we need the magnitude in order to write the vector in this form, right? Okay. So draw a little picture of it, and then see if you compute the magnitude. Remember how to compute the magnitude? How to compute the magnitude? Yeah, it's based on the distance formula. Can we summarize it here? What do you do with these coefficients? Well, this is in component. Standard form is the version of component form. So what do you do with these coefficients on the I and the j to compute the magnitude? You square them, add them together, take the square root, right? Okay, so that's probably going to come out to be some funky number. You can just leave it in. Is it going to come out? Yeah. So, so it's probably going to come out to be some weird number, right? Just leave it. Don't simplify it. Just leave it in, square root of some weird number form, right? Okay, and then we'll go from there. So try doing that first. I'm going to go around and just watch it. Can you talk to your classmates, right? Have a secret activity. Remember how to see? So, got two. Got four. Got somebody. The picture really helps. Okay. That's why, you don't see. Oh, okay. Jeez. Um, sort of use the graph paper sparingly that I gave, so maybe work in one corner first. You got other things to draw to. That's not your So now, in your picture, you can go ahead and draw in the direction that, right? Because once you've got the picture drawn, so always is the positive side. Yes, but the positive direction, positive side. Oh, oh, I see. Oh, so, so, oh yeah, all right. So see, once you've got the idea, once you have the idea geometrically, then that makes the that makes doing the arithmetic or or algebra or whatever other things you have to do on paper, the analytical part on paper, that makes it I think easier. Okay, if you understand the geometry, which I'll do. Let me erase this. Let me erase this picture from last time, and we'll use this. We'll try to reuse this set of axes. You don't need really a very, and you don't need a perfectly accurate picture to help you understand the problem, right? So minus 7i plus 5j, right? So we can count off minus 7 in the horizontal direction, right? And then go up 5, right? In the vertical direction. So we'll end up, somewhere up there, right? Depending on the scale that's put on our set of axes, right? So there's the vector, right? This would be the point. This would be the point minus 7 and 5, correct? And the direction of the vector then is the angle formed with the positive side of the x-axis. So this is the angle that the book is usually calling theta. Okay. And so what's the magnitude now of v? So that is what? The square root of the squares of the coefficients here, right? So we have minus 7 squared plus 5 squared, the square root of that, and that comes out to be what? Square root of 74? Yeah, okay. Which 74 is not a perfect square, so we could probably simplify that maybe. a little bit by hand, but let's just leave it at square root of 74. We'll probably have to estimate that using the calculator anyway. No, we really cannot simplify that even by hand. 74 is 2 times 37. And isn't that right? 2 times 37 is 74. And 37 is a prime number. So you can't really even simplify this at all by hand, square root of 74. So we really are stuck with the calculator. All right, now let's recall this formula, right? And let's just fill in what we know into this. Let's just fill in what we know into this formula, right? So we know that, well, let me go down and find some paper here. Some blank paper. So we know, right, that V is, what was it, minus 7I plus 5J, correct? But we want to write that in that expanded form, right, where we can see the direction. So that is the magnitude, which is the square root of 74 times the cosine of the direction times I, right? Plus the magnitude, which is square root of 74, right, times the sine of the direction times J. So these two things are equal to each other, and they're both linear combinations of I and J, right? This is a combination of I and J. This is a combination of I and J. So you can equate the coefficients here. So what you know is that minus 7 has to be equal to the square root of 74 times the cosine of theta, right? And also you know that 5 has to be a square root of 74 times sine of theta. And then you can really use either one of these two equations to solve for theta. Okay, you really only need one of them. Let's use the first one. That one turns out to be the most convenient choice in this problem, but I'll show you why in just a second here. So let's use this first equation. So if we solve this for cosine of theta, right, we would get, let me write it in the other direction. So we get cosine of theta is minus 7 over square root of 74, right? Just divided both sides by the square root of 74, but I wrote the equation in the opposite direction. And now we probably do need our calculator, right? Because what we're going to do, of course, is apply the inverse cosine, correct? On the arc cosine. Probably get used to calling it arc cosine in calculus 2. That's fine. So we're going to apply the arc cosine now to both sides, right? So we can solve this equation for theta, right? Remember, these functions are almost inverses of one another, not quite, okay, but close enough that we can say that cosine inverse applied to cosine is just going to be theta. And then we have to figure out, well, what is the inverse cosine of minus 7 over the square root of 74? And that's where you're going to have your calculator, right? Okay, to help you. Let's see if I can do that here on this calculator. So I have 7, right, divided by let me put some parentheses in there, 74 square root. And so that comes out to be positive 0.8, but I need to change the sign, right, because this was negative. So let's change the sign. So we have, this turns out to be minus 0.81, right, approximately. And I want to know what's the inverse cosine of that number, correct? So let's go up to our trig, and I think it's second here, inverse cosine, and it comes out to be 144.46 approximately. So that's in degrees. So 144.46 degrees. Does that look like our, let's scroll back up here. Does that look like our picture? See, here's where the picture is really helpful. Does this look like it could be 144.46? Has a good chance, right? It's in the second quadrant, right? So that's encouraging. Okay, so I'm hopeful that that I got this right. You may not need all those decimal places in WebAssign. Remember, it's usually going to give you instructions on how many decimal places you want to use, right? So follow the instructions there carefully and follow the instructions there carefully in WebAssign. Oh, there it is, right? We did it. So we found out the magnitude is square root of 74, and there is the direction. So in our standard form here, we can write v as apparently square root of 74 times the cosine of 144.46 degrees, right? Times I plus, and then same thing with sine, right? Square root of 74 sine of 144.46 degrees times j. And see, that's a little bit, that certainly is a lot messier than writing just minus 7i plus 5j. But remember, the advantage to this is you have two pieces of information now about the vector. You have the magnitude, right? And you also have its direction. So you know there a little bit more about the vector than when it's written just as minus 7i plus 5j. Okay, so now what, but now let's look here. What if you had used sine? Okay, so what if you had solved this equation because you didn't like negative numbers or something like that, right? So, of course, you would have gotten here sine of theta is 5 over square root of 74. So, okay, that looks all very innocent, right? And so you would have applied the inverse sine to both sides. And that's the correct procedure. Okay, and so now we would think, oh, theta is the theta is sine inverse of 5 over square root of 74. But that is going to go a little bit awry, I think. So let's try that. Let's clear this. 5 divided by, let me insert some parentheses here, 74 square root of 74, close that. And so I get 0.58 approximately, right? And now, and that's what 5 over the square root of 74 is. And now I just want to compute the arc sine of that, right? So let's put in arc sine, and whoops, it comes out as 35.53. So, or 35.54. What went wrong? That's right. Yeah, it's not, nothing went wrong, right? Okay. Remember the range of the inverse sine is limited, right? The sine and the inverse sine are not true inverses of one another. Okay. They're not truly inverses of one another. The sine function really does not have an inverse function because it's not one-to-one. Okay. It's not a one-to-one function, right? You know, it's periodic, right? So it's not a one-to-one function. So it really doesn't have an inverse. But we want it to have an inverse. So what we do in trig is we limit the domain of the sine function. That's called the restricted sine function. And the restricted sine function does have an inverse. Okay. How do we limit the domain of the sine function to get the restricted sine function? We limit it to minus pi over 2 to pi over 2, right? The normal domain of the sine function is all real numbers, but to get a function with an inverse, we limit its domain to minus pi over 2 to pi over 2. So it's not quite the same as the true sine function, right? That's why it's called the restricted sine function. That has an inverse. And when you write arc sine, that's really the inverse of the restricted sine function, not really the original sine function. So that's what's happening here. So I said what the domain of the restricted sine function is minus pi over 2 to pi over 2. So the range of the inverse sine function, is minus pi over 2 to pi over 2. So we ended up with an angle from minus pi over 2 to pi over 2, including the first quadrant. Okay, so it gave us an answer in the first quadrant, even though the answer we really want is not in the first quadrant. So what you have to do is you have to figure out what the correct angle is, right? Because you know you want an angle where in the second quadrant, right? But this gives you an angle over here in the first quadrant. What was it? I already forgot. 35 point something. Yeah, 35.54. So it gave you this angle 35.54. But you know the correct direction is really in the second quadrant, right? So you know you want an angle over here in the second quadrant. What do these two angles have in common, right? Well, you're looking for the angle in the second quadrant whose reference angle is 35.54. The reference angle is 35.54. So in the second quadrant, we want this angle whose reference angle is 35.54. So what big angle is that? Well, just take 180 and subtract off 35.54, right? That would give you the angle that you're really looking for. Guess what that comes out to be? I think it comes out to be 144 point something. 140, what? 144.56 or something? 0.46? Is that the right angle? Yeah. Oh, there it is. Yeah. Okay. All right. So, oh, you see, it was a little bit harder using inverse sine to find the direction. So that's why it's good to draw a picture so you won't make these inadvertent mistakes. If you looking at inverse sine, I really need an angle in the second quadrant because my vector's in the second quadrant. So how am I going to fix this answer? How am I going to fix this answer right to get the right angle? Am I going to fix this answer right to get the right angle? Okay. All right. So there's how you finish off that example. Let's see. I think we're going to try that again in and one more time here, just in a little bit more difficult setting, but really the same problem. So example 3 says, find the standard form of a vector v, but you're just given some information about v. So you're really not given all the information you need here about v. So what information are we given? It's really strange. You're told that if you take u, take this other vector u and add it to v, the magnitude of that sum, remember that's also called the resultant vector. So the magnitude of that resultant vector will be 6. Okay, so we don't know what the vector u is either. All right, we don't know what the vector u is either. But if we add it to this vector v that we're looking for, the magnitude of the resultant vector will be 6, and the direction of the resulting vector will be 2 pi over 3. Well, there's a nice angle for us, right? Because that's a special angle, right? But now we are given information about u, okay, fortunately. And we're told the magnitude of u is 4, and the direction of u is pi over 6. So if you're given this information, you are really given the standard form of u. You're really being told everything you need to know about u, right? Okay, because remember, in standard form, you can write u as its magnitude, right, times the cosine of its direction times I, right, plus its magnitude times the sine of its direction times j, correct? Well, they gave you the magnitude and they gave you the direction is pi over 6. So you can fill in everything in this equation, right? So we do completely know the vector u. Let's see. So what's it going to be? 4 times the cosine of pi over 6, right? And then plus what? 4 times the sine of, oops, I left off the I. That's easy to do, by the way. sine of 4 times sine pi over 6 times j, right? So if we can just remember what cosine of pi over 6 is and what sine of pi over 6 is, then we're in great shape. Oops, I know what I forgot. Forgot to bring you our little cheat sheet for special angles. Okay, so I'll try to remember that for next time, but let's see if we can remember it now. Do you remember exactly what cosine of pi over 6 is? So pi over 6 is 30 degrees. Do you remember the cosine of 30 degrees? Yes, that's perfect. Yeah, it's square root of 3 over 2. Excellent. All right. And plus, and then, well, what about the sine of pi over 6? That one's even easier. What? 1/2, right. So we get a pretty easy here vector for u. It's just going to be, since the 2 divides into the 4, right? You just get 2 times the square root of 3 times I plus, and then here, right, 4 over 2 is 2j. So not a, not a complicated vector, right? Of course, in the first quadrant, right, because its direction is 30 degrees, pi over 6. Now, how can we use this information? How can we use this information then to determine v? Because that's what I want to know is this vector v, not the vector u, right? But the vector v. But look, we know something about u plus v, right? And if you take u plus v and subtract off u, that would leave you, of course, with just what? V, right? Okay. So we have kind of a backwards way, right? A roundabout way of figuring out v if we can figure out what u plus v is and then subtract off u, which we already figured out, right? Okay. So we already know what u is in standard form. If we can figure out u plus v in standard form, we just have to subtract off u, and what would be left is vector v that we're interested in. But I think we've got enough information here, right? Figure out what u plus v is, correct? Because we have the magnitude and we have the direction. So again, anytime you have the magnitude and direction of a vector, right, you're going to be able to write down the vector in standard form, right? Standard component form. So let's see. So we know that u plus v must be 6 times the cosine of 2 pi over 3, right? Times I plus 6 times the sine of 2 pi over 3 times j. So it looks like u plus v is going to end up in the second quadrant. And now we just have to remember what the cosine of 2 pi over 3 is. So remember pi over 3, because that's going to be the reference angle, right? The 2 pi over 3 is going to have a trig value similar to pi over 3, correct? You remember what the cosine of pi over 3 was? It's 1/2, right? Remember, we just figured out, or someone told us, right? Cosine of pi over 6 was square root of 3 over 2. So that's a strong clue, right? The cosine of pi over 3, which is 60 degrees, is going to be 1/2, right? So, so that's nice. So we get 6 times 1/2 times I. This one's probably going to be ugly, right? Oops. I've got to fix the sign though, right? Because we're in the second quadrant with 2 pi over 3, correct? So what's the sign of cosine in second quadrant? Negative. Yeah. Okay. So because remember the x-axis is negative in the second quadrant, right? And remember cosine is associated with the x-axis. So the cosine of 2 pi over 3 is minus 1/2. We won't have that problem with sine though. In the second quadrant, sine is still positive, right? Because the y-axis is positive, the second quadrant, and sine is associated with the y-axis, right? So I have 6 times, but I do have to figure out what sine of 2 pi over 3 is. That must be what? Square root of 3 over 2, right? Okay. The reference angle is, again, pi over 3. So the sine of 2 pi over 3 is going to be similar to the sine of pi over 3, which is square root of 3 over 2. And the sign is still positive again because we're in the second quadrant. And then times j here. So let's see, how does this simplify? It looks like minus 3i, right? And this is what? Plus 3 times the square root of 3, right? Times j. So let's see now, what was my formula now? I said we had to take u, to get v, we have to take u plus v. So now we know what u plus v is. That's minus 3i plus 3 times the square root of 3 times j. And then we do what? Subtract off u, correct? So let's be careful about subtracting off u. Let's put it in parentheses because it's got two terms. So we have 2 square root of 3i plus 2 j. And now all you're left with is, this is kind of an algebra problem, right? You're going to add like terms together. So you're going to add your I coefficients together, right? And you're going to add your j coefficients together. And that will give you the coefficients, the correct coefficients for the vector v, right? So I have minus 3 in this coefficient, and then this coefficient is minus again, right? Because of the minus sign outside of the parentheses. So it looks like it's minus 3 minus 2 times the square root of 3. Don't worry about getting a decimal approximation. Just leave that in exact form. I don't think we need the decimal approximation here for any reason. And this is times I, correct? I almost wrote j there. Yeah, see, those are the coefficients on the I vectors, right? And then what's the coefficients on the j vectors? Well, one of them is 3 square root of 3, right? And what's the second one? Minus 2. That's times j. That's it. In exact form, there's what the vector v looks like. Now, for some reason, you need decimal approximation, right? You'll have to use your calculator to figure out a decimal approximation for square root of 3 and for square root of 3, right? So that you can get a decimal approximation, but otherwise, no need to do that, right? We just leave it in, just leave our answer there in exact form. Okay, there's a problem just identical to this in the homework. So probably the next to the last problem or third to the last problem. So be looking at the notes, right, when you're doing this, so you can remind yourself, right, of how to do this. Okay, this problem is completely different. I don't think we need any trig here, but now we do need to know some calculus. So finally, we get to see a little bit of calculus here in Calculus 3. We'll just see it briefly here. Okay, still going to be a while before we dig into calculus in any sort of meaningful way. All right, so here I have a graph of this very simple curve. This is, you know, the just the standard quadratic, just a standard parabola, right? Just y equal x squared is the equation for this curve. That's called a parabola, right? Remember the graph of y equal x squared? So very simple curve with a simple equation there. And of course, that curve contains the point 2, 4, right? You can check that easily just by, you know, plugging 2 in for x, and 2 squared is 4, right? So you know that point, that curve passes through the point 2, 4. Now, what we want to find is a unit vector that's perpendicular to this graph at this point. All right, so I want to find a unit vector that's perpendicular to this graph at this point. You can write the unit vector in standard form or in component form. All right, once we find that unit vector. Now, the first question that probably comes to mind here is, what does it mean to be perpendicular to this curve? Because perpendicularity is a concept that applies to straight lines, right? We can talk about two lines being perpendicular to one another because they'll be perpendicular if they meet at a 90-degree angle, right? But what do we mean to be perpendicular to a curve? Right? That concept doesn't normally apply to curves, all right? Well, the answer is you can make it apply to curves, right? By thinking of the curve at this point, as being the same as its tangent line at that point, okay? So let's just scribble that in. Let's see if I can do this carefully. Probably not going to do it very good. All right, so, well, that could be better, but could be worse too. All right, so what I've tried to draw there is the tangent line to the curve at the point 2, 4, right? Okay, see, that's why tangent lines are so powerful. They allow us to think of curves as straight lines. And the reason we want to do that is because lines are simple, right? But curves are not always simple. Right. Well, of course, a curve isn't a straight line, so you cannot completely treat a curve like a straight line. That's not possible. But at a particular point, at just one tiny point, right, one infinitesimal point, you can think of a curve as a straight line, and the straight line will be the tangent line to the curve at that point. Okay, so so this is the magic of calculus, right? If you take that curve, y equals x squared, right, and you zoom in just at that point, right, very close to that point, so you have to really magnify the curve, right, around that point 2,4, that curve is going to look like a straight line when you zoom in close enough. You're not going to be able to tell the difference between the curve and a straight line. And the straight line that you're looking at there, when you zoom in very closely, is really the tangent line to the curve at that point, right? Now you understand, however, what perpendicular means, right? When we say perpendicular to the curve, we mean perpendicular to the tangent, right? So I want a vector that's perpendicular to the tangent line at this point. Now, vectors are not lines, okay? Vectors are not lines, right? Okay, but in this picture, you can sort of think of that vector as being a line, right? Okay, if you draw a picture of that vector, you know, you get something that looks like a straight line, correct? Okay, so you want that that line that's kind of imitating the vector, right? And you want this tangent line that's kind of imitating the curve. You want them to be perpendicular to each other, okay? So what is the relationship now between perpendicular lines? So what's the famous relationship between perpendicular lines? So how do you know that two lines are perpendicular, you know, other than just looking at them and sort of they look perpendicular, which might be misleading, right? Huh? Well, they meet at, yeah, perpendicular lines meet at a 90-degree angle, right? Okay, they meet at an orthogonal angle, a 90-degree angle. So so they meet at a 90-degree angle, but analytically, how can you tell that the angle that they're meeting at is 90 degrees? How do you know it's not 89.9 or 90.1? That's right. Yeah, there's a relationship between their slopes, right? Okay. And the relationship is the slopes have to be negative reciprocals of each other. Okay. So if you have two perpendicular lines, the slope of one line and the slope of the perpendicular line, they have to be negative reciprocals of one another. If that's true, then you know the two lines are perpendicular to each other. Okay. And you can prove that with a little bit of geometry. Okay. So so that's what we're looking here for, are negative reciprocal slopes. Now, but how do I even find the slopes, right? Much less negative reciprocal slopes. So let's start with the tangent line. How do we find the slope of this tangent line that I've got drawn in here? That's where calculus comes into play, right? Okay, so how do you find the slopes of tangent lines in calculus? The derivative, right? It's the derivative, right? Okay, so the derivative is all about slopes of tangent lines, correct? Okay, in fact, the derivative of this curve at this point the derivative of this curve at this point, that numerical value is the slope of the tangent line at that point, okay? Right, so that's what your Calculus 1 instructor spent the first 8 weeks of the semester trying to drum into your head, right? Okay, slopes of tangent lines, derivatives of curves, those are identical concepts, right? Okay, so if we can find the derivative of this curve at this point, then we'll know the slope of this tangent line that I've got drawn here, right? Okay, all right, so how do we find the derivative here of this curve at the point 2, 4? Let's see, how do I write that in notation? So that would be dy over dx, right? This is the old-fashioned notation. At what? X equals 2, correct? So I want to know what is the derivative at x equals 2. But to get the derivative of x equals 2, I need to know what the formula for the derivative is, right? What is the formula for this derivative? So what is dy over dx in general? 2x, sure, right, okay? So that's a very simple function to differentiate, right? The derivative is 2x, right? So that derivative evaluated at x equal 2, that is 2 times 2, right? Which is 4. So the slope of this tangent line, is 4. Let's call that m sub 1. So that is 4. Okay, guys, so now you can answer part 2 for me here. We've done now this part, okay? We found the slope of the tangent line at 2, 4. So what's the slope of the quote-unquote normal line? That means the line perpendicular to the tangent line, okay? So you know, a tangent line is a tangent line. A normal line, if you've not heard that term before, you probably haven't. But a normal line is a line perpendicular to a tangent line. Okay. In calculus 1 and 2, sometimes you're asked to compute normal lines. Usually, it's in a homework problem, and then the question doesn't go anywhere. Okay, so it's just kind of like an exercise. But in calculus 3, normal lines are going to be very important to us because they're going to be very useful. So we're going to be working with normal lines quite a lot. Okay, so this is your first chance there to hear that term normal line. I don't know what makes it normal, but that's what it's called, the normal line. So what is the slope then of the normal line? Negative 1/4, right? Because that's what we discussed earlier, correct? The slopes of perpendicular lines are negative reciprocals of one another. So let's call this m sub 2, just to distinguish it from the slope of the tangent line. That slope is going to be minus 1/4. Okay, that slope is going to be minus 1/4. So now can you, since you know this slope is minus 1/4, can you find a vector? It doesn't have to be a unit vector, but can you find a vector that looks like the vector in this picture? That looks like the vector in this picture. So it has its initial point 2, 4. So I want to know what would its terminal point be, so that I would end up, if I computed the slope of that vector, quote unquote, I would end up with minus 1/4. Can y'all tell me another point here then? Or maybe the terminal point of a vector that would have the right slope? So sort of, how could I draw this picture with initial point of a vector 2, 4, some terminal point. Yeah, any magnitude you like. That's what I said. It doesn't have to be a unit vector. Um, David, why does it not have to be a unit vector at this point? Yeah, ultimately, I think the question said find a unit, but why can't we just start with magnitude 1? And if you have a vector, how can you take that vector and sort of turn it into that turns it into just a vector in component. But how do I make it? How can I make it? How can I make it? I mean, no. No, I don't need to set anything to 0. What do I do? Yeah, you said it. Say it. Divide by what? Yeah, divide by its magnitude. So if you take a vector and divide both components by the magnitude, you'll get a unit vector in the same direction. The unit vector in this, it'll have the same direction, okay, but its magnitude will. Okay, all right. So my point was here: if I can get any old vector that kind of looks like this vector that I've drawn here, right, then I can turn it into a unit vector. So it can be, David, you're right. It can come all the way over here if I like. All right. It could even actually go in the opposite direction if I wanted it to. Okay. I just need some vector, and then I can make it into a unit vector. So can you figure out how to write some vector here that would give us the same slope as minus 1/4, right? If you were drawing a line, and starting from this point, and you knew you wanted that slope to have minus, the slope of that line to be minus 1/4, how could you find another point on that line? Sure, right, yeah. You have to go back and use the very old idea of how you compute slope, right? As rise over run, right? Remember that? So you can think of the minus 1/4 as being minus 1 over 4. You could also think of it as being 1 over minus 4. Okay. But this is a little bit more convenient. I'm sorry. The first one is a little bit more convenient because that tells us, right, that if we have any point on that line that has this slope, if we start that point and go down 1, right, and to the right 4, that will bring us to another point on the line, correct? Okay. So if I'm at the point 2, 4, right, and I go down 1 and over 4, where would that take me? So let me erase this because what now? So I'm at 2, 4, I go down 1. So that would go to 3, right? And over 4 would take me to 6. Is that right? So where is that? 3 and 6. Oh boy. I didn't draw this very well, right? Here. You have to look at the scale that I drew these axes. I didn't draw them very good. This point? What are the coordinates of that point? See, we went down 1 and over 4, right? So that's 6 and 3. So if you have this vector with initial point 2, 4 and terminal point 6, 3, I think that vector is going to be perpendicular to this curve. Because if you compute the slope between these 2 points, you get minus 1/4. That's definitely not a unit vector though, right? Okay, definitely not a unit vector. So y'all do that for me. Unitize that for me, okay? So take that vector and turn it into a unit vector and also write it in standard form. That's with I and J. Okay, so this vector that I've got pictured here, turn it into a unit vector, but also write it in write the unit vector in I J form. Okay, can you all do that? All right. So you've got these 2 points. So you turn that into a component vector, right? So when you turn it into a component vector, you can write it in I plus J form, and then right to turn it into to give it magnitude 1, divide by the magnitude. That's the term. So just the slope. Yes. Standard. Easy magnitude, not a whole number. Right. So can't really. So, that would be a little bit smaller. It's not really to actually slow. Now, this is right. Here, so this. Yeah, and then do it. All right, guys, very good. Excellent. And now you're all ready for. All right, so when you put this vector that I've drawn here in component form, of course, because of the way we generated this point, right? You really end up with just the slope, right? You get the j component is being 4 and the I component is being -1, right? When you take the difference of these points, because that's the way we generated this point, right? Was by using the slope. So we get that. I think I said label this thing. Was this supposed to be labeled? I don't know. Okay. Oh, P prime. So P prime is going to be what was it? 4i minus j, right? Yeah. So that's what this vector looks like in component form. It's just 4i minus j, or 4 comma -1, right? In component form. And then if you normalize that, I'm sorry, if you put that, if you unitize that, well, the magnitude of this vector is, the magnitude of that vector is square root of 17. So you get the final answer here. P is 4 over square root of 17 times I minus 1 over square root of 17 times j. So that seems like a very obscure exercise, right? To do that. But again, in calculus 3, these so-called normal vectors, these perpendicular vectors, are going to be very useful to us. All right, we've got 2 more examples now from this homework, and they both involve physics. All right, so that makes them a little bit confusing to understand, but the mathematics turns out to be very simple. So if you sort of just accept the physics, as what's being described to you, okay, then the mathematical part of it is really pretty easy. Okay, the problems look harder than they are. Okay, just because the physics seems a little bit mysterious as to why the physics is working like it is. All right, so we just have to take that as a given, and then but the mathematics will be straightforward. Okay, let's stop there for a second though, and let's take about 5 minutes here. And I forgot to pass out the roll, so first thing we have to do when we come back is pass out the roll. So remind me to do that. And let me stop the tape here for a second. Just pause it. One thing about WebAssign to remember, right, is if it wants decimal approximations, it will usually say, write your answer to 2 decimal places or 3 decimal places. If it doesn't say that, then probably it wants exact answers. That means not in approximate form. So you would just type in your answer, as you've written it down on the page, and not try to approximate any calculation there, like a square root or a cosine or sine of a number. You wouldn't try to approximate those. You would have to leave the square root or leave the sine and cosine in your answer. So that's typically the way WebAssign is working. That's another thing that can get frustrating on when you're typing an answer. So that's another thing you can send to me. Do ask your instructor, and because I know what the right answer is. So if you're making a formatting mistake, I can help you with that. Okay. One of the things now that Well, two of the real common applications of vectors are force and velocity. We're going to start with force here. Force is, you can think of that as a push and pull on an object, right? It changes the object either into a state of rest, into a state of motion, or from a state of motion, it puts it into a state of rest, right? So, force, you can think of it as a push or a pull on an object. But the reason vectors are so useful for force is there are really two components to force, right? There is the actual quantity of the force, right? The amount of force that's being applied, and often this is measured in weight measurements like pounds or kilograms, right? So there's the force that's applied, but force is applied in a direction, right? So when you're in a particular direction. So when you're discussing force, right, or trying to do calculations with force, you need to incorporate the amount of the force plus the direction of the force is important as well. And so that's why vectors are useful to represent force, right? Because we can there are two measurements, right, that are incorporated into vectors, right? There's the magnitude of the vector, but also there's the direction of the vector. So and velocity is very similar, right? As well, right? Velocity has there's an amount of velocity, right? A quantity of velocity, but there's also direction in velocity as well, right? In which direction is the motion occurring? We're going to see examples of both of these things. All right, but let's start with a very simple force example. So again, now, unless you're really curious, don't try to wrap your head around the physics of force. Okay, just take it as a given here in the math class that vectors are useful in representing force, and then you can harangue your physics instructor about why that's the case. Okay, all right. So two tugboats are pushing an oil tanker through the ship channel, as shown in this picture. And of course, to push the tanker through the ship channel, the tugboats have to apply force, correct? So here is how they're applying this force. So one of the tugboats is pushing in this direction at a force of 400 pounds. And then in a symmetrical fashion, otherwise we're going to get that tanker lodged in the ship channel like that. Remember the tanker that got stuck on the sandbar in the Suez Canal and caused such a commotion for several weeks, right? Otherwise we're going to get the tanker stuck in the ship channel. So the other tugboat is applying force in a symmetrical fashion to keep this tugboat moving, well, in this picture, moving horizontally to the right, right? Okay, so this tugboat is applying force in this direction, 400 pounds of force. This tugboat, the second tugboat, this is labeled as tugboat 1. So tugboat 1 is applying 400 pounds of force in this direction, and tugboat 2 is applying also 400 pounds of force in kind of a symmetrical direction, right? So that we can keep the tanker moving directly to, in this picture, directly to the right. Okay, so the question though is how much force altogether is being applied to the tanker? Okay, so this tugboat is pushing with 400 pounds of force. This tugboat is pushing with 400 pounds of force, but they're not pushing the tanker. Notice they're applying the force in a particular direction, right? Okay, they're not pushing the tanker. Either one of them is not pushing the tanker directly to the right, correct? Right. This tugboat is pushing it in a slightly different direction. This tugboat is pushing also in a slightly different direction than just due east, sort of here in this picture. So that means then that the total force that's being applied to the tanker is not going to be the 800 pounds. Okay, right? The actual force being applied from this tugboat is not quite um, um, well, let me say that. Let me just say what I said, right? Okay. The total force being applied to the tanker is not just quite 400 plus 400, all right? Because of the direction involved in how the force is being applied. All right. So, how do we figure the amount of force that's being applied actually to that tanker? Okay. And the answer here is very simple. You can represent this force, okay, being applied by this force being applied by the first tugboat. You can represent that as a vector. Okay. And the magnitude of the vector is going to be the force applied by this tugboat. Okay. And the direction of that force, the direction of that vector is exactly what you see in this picture, correct? So you can represent this force from tugboat 1 as a vector. And that's what we're going to do here, right? So that's very easy to do, okay, right? Because you know the direction of this force, right? It's 20 degrees because they very nicely have shown us, right, in the picture that that the direction of this tugboat, right, is 20 degrees. So you can think of the the force applied by this first tugboat just as this vector, the magnitude of the force, which is 400, right, times the cosine of the direction, plus the magnitude of the force again times the sine of the direction. Same thing for the second tugboat, except the direction is a little bit more complicated, right? Okay. So again, the force here applied by this tugboat is 400 pounds, right? Okay. The amount of the force. The direction, though, as shown in this picture, is minus 20 degrees. Now, that is an angle from the x-axis, so you can use minus 20 degrees as the direction of this force. But if you wanted to, if you were just insisting on using positive angles, you could also measure the angle, the direction this way as well. Okay, you'd end up with 340. Right. But let's go ahead and use the minus 20 degrees like they have in the diagram. So here's the force corresponding to the second tugboat, right? Okay, its magnitude is 400 because that is 400 pounds of force being applied, and its direction is minus 20 degrees. So just write the magnitude, right, times the cosine of the direction times I, right, plus the magnitude times the sine of the direction times J. Now, the question that we're interested though is, again, what's the total force being applied to the tanker? Okay, so what is, what's kind of like this force vector that is acting on the tanker? And that's very so. This is why I guess physics. Physicists love vectors, right? Because the answer turns out here to be very simple mathematically. It's just the sum of these two vectors, right? Okay. The resultant force on that tanker is just the sum of the individual force vectors. So all we have to do is add together F1 and F2, and that would give us the force here acting on the total force there acting on the tanker. I hope that direction of that force acting on the tanker, I hope that direction is, what direction do I want that to be? What would the direction of that vector be? If this tanker is moving directly to the, I want it moving directly to the right. So what would that what would the direction of that? What? 0, right? Yeah. So I'm hoping, I'm hoping that the direction angle for this vector turns out to be 0 when I add these two things together. If it's not, then you know, we're going to have the tanker going in some strange direction, right? Okay, so let's add these two things together. So that should be pretty easy to do, right? Fortunately, the magnitudes are all the same, so that's nice, and the angles are also very similar. So I'm hoping that this this arithmetic of adding these two force vectors will be pretty straightforward. Let's see, and it's made a lot easier by the fact that let's see, cosine of 20 degrees and cosine of minus 20 degrees, those are the same, right? Aren't those the same cosine? Because this is in the first quadrant, and this is the corresponding angle in what quadrant? That's in the fourth quadrant, right? Okay. And cosine, though, is positive in both the first quadrant and the fourth quadrant, right? Because remember, cosine goes with the x-axis, and the x-axis is positive in the first quadrant and the fourth quadrant. So these two cosines are really the same, even though this is 20 degrees and this is minus 20 degrees. That's really the same cosine. So when you add these two things together, you'll just get 800 times the cosine of, you can either write 20 degrees or minus 20 degrees, your choice there, okay? Times I, okay? So I'm going to use positive 20 degrees. Now, why not use positive 20 degrees instead of negative? Now, what about these J terms, though? What's going to happen here? Well, a nice thing happens here as well, because the sine of 20 degrees and the sine of minus 20 degrees are opposite of each other, right? Okay. Isn't that correct? Sine is positive in the first quadrant, but in the fourth quadrant, it's negative. So these two signs are just opposite of one another. So guess what's going to happen when you add these two terms together? They cancel, right? They just cancel exactly. So you're left with, there it is, 800 times the cosine of 20 degrees times I. That's it. Okay. What direction is that? That's horizontal, right? Because that's just a multiple of the vector I, right? The horizontal vector I. So indeed, we're lucky that tanker is moving horizontally, right? And now but what force is being applied to it? It's 800 times the cosine of 20. Can y'all calculate that for me? What is 800 times the cosine of 20 degrees? What does that end up being? It's pretty high because cosine of 20 degrees is pretty close to 1, but what? 751? There we are. All right. So almost 800 pounds of force, right, being applied to the tanker, but not quite. Okay. Only 751. And that's again because these tugboats, right, are moving at an angle, right? So the resultant force is really just 701 pounds, okay, instead of 800 pounds. But fortunately, the tanker is moving in the right direction. All right, let's try another one. Now, this one involves velocity, but we're really going to treat the velocity very similar to force, okay? I do have to explain one thing to you, though. In surveying and navigation, a bearing, right? So you've heard that term in navigation, right? A bearing. That's the direction clockwise from north, okay? So when you measure a bearing, don't quite measure it like we measure angles in trig, okay? We measure it clockwise from due north, clockwise from due north. So that becomes important in this example. All right, so an airplane is traveling at 500 miles per hour, and it has a bearing of 330 degrees, okay? So what that means is clockwise from due north, the angle of the airplane is 330 degrees. So if you measure from due north clockwise, you get 330 degrees, right? Well, in trig measure, right, since we're going clockwise, this would be, in trig measurement, this would be an angle of minus 330 degrees, right? And this, of course, this angle in the counterclockwise direction from due north would be 30 degrees, okay? So that would, in trig measurement, we would say that's that angle that I've drawn there is positive 30 degrees. Okay, now, so you know, pretty easy setup. But now the problem is there's wind, correct? So it says when the plane reaches a certain location, it encounters a wind, and the wind has a velocity of 70 miles per hour. And it says the wind is in this direction. That's not a bearing now, okay? So that's a meteorological direction. And what that means is, when it's written like this is 45 degrees east of north, okay? 45 degrees east of north. Well, of course, this is, you know, we're assuming in the picture, right, straight up is north, correct? So 45 degrees east of north means the wind is kind of coming in like this, right? Across the path of the airplane. See, this is right here is north. All right. So this is 45 degrees east of north. So in the east direction, right, from north. So if we measure that angle correctly, this is 45 degrees. Okay, so what's going to happen to the airplane then in these conditions? It's going to get slightly diverted, right? Okay, because it's got the wind acting on the plane. All right, so the path of the plane is going to get shifted a little bit in this direction, right? So the plane's going to get moved over a little bit because of the wind. And probably what else is going to happen to the plane? It's going to get slowed down. That's right. Okay. So the velocity of the plane is going to change as well. All right. So what we want to know is, what is the resultant speed of the airplane and what is its direction? All right. So how is the plane actually moving, right? Under the force of this wind. All right, so that seems like a really complicated problem, but it turns out with vectors, it's not, because both of these sort of forces here that are being described in the diagram, you can simply represent them as vectors. And then when you add those vectors together, the sum or the resultant of those two vectors will give you the speed and the direction of the airplane. All right. So with vectors, this turns out to not be a difficult physics problem at all. Let's see if we can write down these vectors quickly, and then we'll probably have to finish the problem next time. But so let's just show the vectors, but the vectors are very easy to write down, right? Okay, so here's the vector representing the airplane, all right, which has a velocity and a direction, right? Of course, the velocity is going to be the magnitude of this vector. So that was 500 miles per hour, correct, right? And the question is, what is the proper direction? Let's make sure we measure direction according to the way we want to do it in this class, right? Not according to a bearing. So the bearing of the plane was 330 degrees, right? So that was 330 degrees from due north. What's this angle, though? Well, remember, if this is 330 degrees, that means you it's almost one rotation, right? But 30 degrees short of one rotation, correct? So if you take this angle plus that 30 degrees that you were short of one rotation, that gives you 120 degrees, right? So this angle is 120 degrees. The angle from the x-axis in this picture is 120 degrees. So in our measurement, the direction of the airplane is 120 degrees, okay? So that's the direction of the vector that corresponds to the airplane. What about for the vector that corresponds to the wind now, right? Because the wind isn't exerting a force, correct? In a particular direction. Again, very easy to write down, right? Okay, so the speed of the wind was 70 miles per hour. Want to make sure, by the way, that these units of measure are corresponding. So this was miles per hour. This was also miles per hour, right? What about the direction of the wind? In our measurement of direction, we have to be careful about that. So see, here's a little vector that's sort of representing the wind, right? Okay, what is its direction in our measure of direction? Let's superimpose an x-axis here, right? So what is this angle? It's 45 degrees again, correct, right? Okay. If this angle was 45 degrees, then this angle also has to be 45 degrees, right? Because those have to add up to an orthogonal angle, right? A 90-degree angle, correct? So so that's easy. The wind direction is 45 degrees, which was sort of what was described to us in the problem. So there's the vector that corresponds to the wind. The resultant force on the airplane now is just the sum of those two vectors. It's just that easy, see? Okay, so all you have to do is add these two vectors together, and that will give you the resultant vector, which is going to tell you how fast the airplane is going by its magnitude and also its direction. Okay, all right, so we have to figure out how to add these two things together, though. Okay, well, I think that's going to take a little bit of calculator, right? Okay, to add these things together. Once we have the resultant vector, then it's going to be pretty easy to understand what the magnitude is. So that will give you the new speed of the airplane. What's going to be a little bit tricky to understand is the direction. So we have to go through all those steps of figuring out the direction, the angle of the new angle of the airplane. That's going to involve using inverse cosine or inverse sine again, right? So that's going to be a little bit of work because the arithmetic is going to be a little bit messy, but it's not going to be challenging. So we'll try to finish that one next time because we're out of time today, but that'll all be just sort of arithmetic, right? Okay, conceptually, there's what's happening. I think you have a problem like this in your homework. The very last one, got three forces acting on some object. To find the resultant force on the object, just add the forces together. That's it. Okay. All right. So see you guys on Wednesday. Oh, got to roll again. I'll have to do it. Okay. Someone's gonna have to have a designated reminder. So I'm gonna tell somebody on to you have to remind me. Okay. See you guys.